Okay, if I pick up where I left off and continue on, a few graphs to go. How about this graph? This graph only requires 2 circles. There, let's see, these are the circles. Notice how this game is played. Now, we did mention up there, if you remember, we said if you touch the angle, if this angle is odd, you get that many odd leaves. If the angle is even, you get double those. Let me show you how we're going to graph this. We're going to do it 2 times. One time we're going to graph this, picking them point by point, not that much to really do. R equal to 1, 2, and negative 2. And I suggest you do at least one of those from scratch, not using the shortcut I'm going to tell you. Graph of a sine wave starts at the origin, runs up to the amplitude, back down to the starting point. And you're done. That is 1 cycle. That is, I forgot, they shrank the, I'm going to shrink this because I need 3 periods to get 1 cycle. And I'm planning on doing all 3. So the first problem, we're doing the very long way. There. But in reality, when I graph it after that, it's going to take me no time using a shortcut. So 1 full cycle is 2 pi over 3. This is half of that, that's pi over 3. This is pi over 6, 2 pi over 6, 3 pi over 6. 3 pi over 6 is pi over 2, by the way. 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, and 12 pi over 6. That's a lot of points. What I need to label. Again, this is not how we're going to graph this. We're going to graph this using a shortcut, and I'll show you how the shortcut looked like. You're going to be very impressed, I think. And let me copy this. Okay. Oh, not the whole thing. Okay, no problem. Now I could force that to move a bit, and maybe I could fit it here again. Did it overlap? Yeah, it overlap. Okay, we could shift this even a bit more. How about now? Better, somewhat. Okay, that's good enough. For now, this is what we're going to do. I'm going to take the first piece and let me start graphing. At 0, I am at 0. I'm right there. Increases. By the time I reach pi over 6, I am at 2. There's pi over 6, and there's 2. A smooth curve. And it's going to come back down. It's going to hit 0 by the time I reach pi over 3. There's pi over 3. It's going to come down and hit 0 before I pass that. There it is. Now, between pi over 3 and pi over 2, r is negative. Between pi over 3 and pi over 2, r is negative, so I'm right here. It's going to decrease. By the time I reach pi over 2, I am at negative 2. There's pi over 2, and isn't negative 2 right there? And then what? Then it's going to increase back, but it's negative still. By the time I reach 2 pi over 3, I am at 0. There's 2 pi over 3, and there's 0. Since it's negative here, so I'm right here. Remember, this is a connected graph, so it's going to pick up and go back and zero out. Now, I don't need all of these points that are labeled, but I wanted to label all of them to make sure you see it. Now, if I go for between 2 pi over 3 and 5 pi over 6, 2 pi over 3 and 5 pi over 6, r is positive. By the time I reach 5 pi over 6, r equal to. There's 5 pi over 6, and there's 2. And then it's going to decrease back. By the time I reach pi, I am going to hit 0. There's pi, there's 0. And can you guess what happens after that? Between pi and 7 pi over 6, between pi and 7 pi over 6, r is negative. I'm right there. It's going to trace. By the time I reach 7 pi over 6, I am at negative 2. There's 7 pi over 6, there's negative 2. Do you see it starts retracing? Do you see how many leaves we have? 3 of them. Now, how are we going to actually graph this? The way we're going to graph this, we're not going to need all of this. We're going to use symmetry, and it's going to make our life a lot easier. This is how we're going to use symmetry. We're going to say, look at the graph of one period, a sine wave, a traditional period. And I don't even know that I need those yet. There, starting from scratch. I'm going to say this is 2 pi over 3, half pi over 3, half pi over 6. This is all I need. All what I need is the pi over 6, and I'll know I should label the pi over 6's. And I know the pi over 6's are right here. There's a pi over 6 right there. And there's a pi over 6 right there. That's all I need. And watch how this works. I'm going to start at 0. I am at 0. I'm going to increase. By the time I reach pi over 6, I am at 2. There's pi over 6, and there's 2. I'm done. Why is that? I know these graphs are symmetric. If it took 30 degrees to get the bottom half, it's going to take 30 degrees to get the upper half. Not only that, if I have this in mind, if I know I'm going to have the sine of 3 theta is going to have 3 leaves. If I know there are 3 leaves, they're equidistant, meaning I take the whole 2 pi and divide it by 3 apart. That's the distance between each petal. So take the first peak. You see where this peaks? Take the pi over 6, add the 2 pi over 3. Why 2 pi over 3? Because I know there are 3 petals. If there were 4, 2 pi over 4. If there were 5, 2 pi over 5. What would that be? If I multiply by 3, multiply by 2, 4, that's 5 pi over 6. The next petal is going to max out at 5 pi over 6. I'll just copy that. Oops, I overdid it. Overdid the top 2. So there and there. Got it. And if I add another 2 pi over 3 to this, so I was at pi over 6, now it's 5 pi over 6. If I add 2 pi over 3, that's 4. 9 pi over 3, that's 3 pi over 2. That's where the next leaf would be. And I don't have to trace all of that graph, but I'll get the same exact graph. Now, that's how we're going to do this. Let's try that analogy, and let's try that analogy on this graph. This is a bit of a challenge. This is not your traditional graph, but again, you're not a traditional student. You're special, right? This has 3 leaves. Let me take out that one. Okay, that'll work. That's perfect. I could shrink that or leave it. So this is really how I'm going to graph. Did I say 3 leaves? I meant I need 3 circles. all what I have to do is go up to 3 and negative 3, 1, 2, 3, and 1, 2, 3. I could trace the graph like I did that top one. I could trace all the points. R equal 3, R equal negative 3. A cosine wave starts on the amplitude, runs down, back to the starting point. Done deal. Labeling is the crucial part. This is 2 pi over 4. Right? This is half of it. This is half of that. So this tells me I need pi over 8. Well, how am I going to do pi over 8? Observe. This is pi over 4. This is pi over 4. What you're going to do, you're going to cut that in half. If you multiply that by a half, so you're cutting those into 8 equal parts. Again, not a traditional graph, but we're going to do it anyways. This is 1 pi over 8, 2 pi over 8, 3 pi over 8, 4 pi over 8, which is pi over 2, 5 pi over 8, 6 pi over 8, 7 pi over 8, 8 pi over 8, 9 pi over 8, 10 pi over 8, 11 pi over 8, 12 pi over 8, 13 pi over 8, 14 pi over 8 if you reduce it, 15 pi over 8, and 16 pi over 8 is 2 pi. Very good. What do I need? All what I need is one of those. Let's say I start this graph. At 0, I am at 3. At 0, I am at 3. Right there. Decreases. By the time I reach pi over 8, I am at 0. Done. I'm done with the whole graph. The bottom half is identical. How many graphs are there? If this is even, this is an 8-leaved graph. I should expect 8 leaves. Okay, that's not coming out with the thick. Let's go with the thin. This is an 8-leaved graph. What that means, they're 2 pi over 8 apart. Wherever the first one maxes, 1, 2 pi over 8, that's the next one. That's the next one. That's the next one. Again, 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 and again. And the graph has to be between those. And this is going to have, believe it or not, 8 leaves. That's when you take a disc and break it into 8 equal parts, like 8 cylinders. Right? There you go. And of course, that first one. That's how the graph goes. So using symmetry to my advantage, I could save myself a lot of work. Now, I'm going to do the same graph one more time, since you liked it so much. But here there's a square. This is the last type of problems we have. Well, I ignore the squared. If I square root both sides, I know r is going to equal plus or minus 3 the square root of the sine of 4 theta. This is how I'll do this. I'll play a game. I know the radius is 3, but if I sketch the graph ignoring the radical completely, the only use I have is knowing it's going to be 3 units above, right? 1, 2, 3, and down 3. And let me show you how that works. A graph of a sine wave. Like the one before, this is 2 pi over 4, this is half of it, and this is half of it. So I know the deal. I did that already. I just finished it too also. And I'm not going to worry about labeling those because they're labeled up there, pi over 8 each. Break this in half. And break this in half. And let's see how this works. In our case here, at 0, I am at 0. Increases. By the time I reach pi over 8, I am at 3. and I come back down. And since this is an even, I'm gonna have a 8-leaved graph, supposedly. Again, I'm ignoring the square. So 2 pi over 8 apart. Add 2. Oops, this one is really slightly tilted off. Not that. Oops. Just itsy bitsy. There we go. So then 2 more, 2 more, 2 more, 2 more, 2 more, 2 more, and 2 more. So the graph looked something like this. Okay, I'm getting really sloppy. Under normal circumstances, this is the graph of R equal. Okay, I can't multitask. Let me focus on graphing first. There we go. This is the graph of R equal 3, the sine of 4 theta. But there's a square there. What does the square do? Well, when you square root both sides, this tells me that this right here must always be positive. Look at this graph. Can you tell that this is negative between pi over 4 and 2 pi over 4, which is pi over 2? Since it's negative there, that can't be there. And these graphs are symmetric, which means the opposite side can't be there either. And since you have one and you skipped one, the next one up, you could continue this if you want to see it. 1 pi over 8, 2 pi over 8, 3 pi over 8, 4 pi over 8, 5 pi over 8, 6 pi over 8, 7 pi over 8, and 8 pi over 8. So between pi over 8, 2 pi over 8, 3, 4, 5, 6, 7, and 8. Between 6 and 8, it's negative. You can't have that. So that's going to make that graph a 4-leaf graph. The square root, if this is an even number of leaves, it's going to cut half of it, and the graph is going to look like this. It's going to eliminate half of the leaves only if it's even. Now, for the trig class, for the calculus class, the 1300, you're not going to see this. But for the second semester calculus class, specifically at Cal Poly, you're going to see this. And what it turns out here, if this is odd, the square doesn't affect the number of petals, only if it's even. So, if I square root both sides, I would know that the square root of 4 is a 2. I need that so I don't have to readjust the whole graph. A graph of a cosine, and this is all we have to do. This is 2 pi over 3. This is half of it, pi over 3. This is half of it, pi over 6. So, pi over 6 is all I need. And here they are. At 0, I am at 2, because I know the square root of 4 is going to be 2 the square root of cosine of 3 theta. So, at 0, I am at 2. Let's say that's 2. At 0, I am at 2. I'm sorry. There's 0, there's 2. Decreases. By the time I reach pi over 6, I am at 0. I'm done. Because I know the bottom's going to take that much. And we know that 3 theta indicate this is a 3-leafed graph. So they're 2 pi over 3 apart. Since this is over 6, make that over 6. 4 pi over 6 apart. Wherever this is, oh no, I'm sorry. This is maxed out at 0, right? So 2 pi over 3 is right here. So 0 is the first max. Add 2 pi over 3. The next one is going to max right there. I kind of made that. This is really not 30 at all. It's more like 15. There we go. Not really. That's more like 30. So then the next one up. And if I add another 2 pi over 3, isn't that 4 pi over 3? That's where the third leaf is. So those leaves are always equidistant. It turns out, labeling this a 2, of course. I did a 4, you could label it 2. It turns out the square does not affect the odd number of leaves, but for the even, it cuts them in half. And that's pretty much it for this section.